Hello everyone, I am Enna and I'll present our work on Rank2Tell, a multi-modal driving dataset for joint importance ranking and reasoning. This work is done at Honda Research Institute US in joint collaboration with Stanford University. The motivation behind this work is to enhance the transparency and trust in autonomous vehicles and also provide assistance to drivers to navigate safely in complex traffic scenarios. To achieve this, it's important for the model to identify critical traffic agents whose behavior impact the ego vehicle's decision making and also provide human interpretable reasoning about these critical agents. Effective scene understanding is important to identify such agents, and this could be greatly enhanced with key features such as 3D map, semantics level information, spatial and temporal relations, agents importance level, actions, intentions, and attention attributes. Identifying important agents further allows for more efficient allocation of computation resources, and assisting drivers with such effective communication can increase their situational awareness. However, there exists no real driving dataset in this domain which can provide comprehensive features to achieve this. In this work, we create the first multimodal dataset Rank2Tell that ranks multiple important agents in complex traffic scenarios, as well as tells a natural language explanation on how these important agents influence the ego's behavior. We benchmark the existing methods on related tasks of importance classification and captioning with our new dataset. As compared to existing datasets, our dataset provides dense annotations of semantics level information, spatial and temporal relations, agents importance level, actions and intentions, along with attention attributes with diverse captions in wide camera view. It comprises of 116 real driving scenarios recorded at urban 4-way intersection at 10 frames per second. The scenarios were captured with 3 cameras mounted on car on front left, front right and front center. The car is also equipped with LiDAR sensor and high precision GPS along with canvas. The annotation strategy is as follows. Given the ego car's intention, speed and history frames information of last 4 seconds, we ask the annotator to identify important agents they should be paying attention to for safe driving. Further, they were asked to rank those identified important agents as high, medium or low important. Also, they had to answer questions corresponding to 4W plus 1H consisting of visual, motion, location, attributes and provide reasoning behind picking the important object in the form of free-form captions. To account for diversity, every frame was annotated by 5 different annotators and every 4th frame was annotated. These are the multiple choice options we provided to annotators for each object type for 4W plus 1H questions. Here is an example of a frame annotated by 5 annotators. The red, yellow and green bounding box show high, medium and low importance respectively as the final importance of agents in the scene. With the intention of the ego car to take right turn at the intersection, the annotators mark the preceding truck and the crossing pedestrian on the right as the high important objects. And these are the diverse captions provided by them. For agents with ID 1, only 3 annotators consider this agent as important. That's why we have only 3 annotators data shown here. Here we show the statistics of the data annotations. The first plot shows the agent's importance level distribution across different agent types. And the second plot shows the agent's importance level at different locations with respect to ego's intentions. Further, we perform inter-annotator consistency analysis by using the mode of all 5 importance level annotations. Here 40%, 60%, 80% and 100% means that 2, 3, 4 and 5 annotators provided the same importance levels. In case of multiple modes, we choose the highest importance level. The consistency analysis shows that 98.61% of data samples have more than 60% consistency for non-importance as mode. Similarly, for low, medium and high importances, 61%, 66% and 88% of data show greater than or equal to 60% consistency respectively. Further, to assess the quality of the dataset, we compute intra-class correlation ICC, which is widely used for the assessment of consistency made by different observers measuring the same quantity. The ICC for our annotations is 0.92, which shows excellent inter-rater agreement. Further, we develop a model to jointly perform importance classification and captioning of important objects on Rank2Tell dataset. It consists of 5 main components. Firstly, the 2D feature extractor uses a sequence of RGB images, depth images, semantic maps, the ego vehicle's inertial data, and a 2D bounding box of each object in the scene. Then the 3D feature extractor leverages the PointNet++ backbone and the voting module in VoteNet to aggregate all object candidates in a scene. To capture mutual influence and relations among objects, we use a relational graph which takes in the concatenated 2D plus 3D object features. The final object features are obtained by concatenating the graph node features with objects' relational features, global features, ego features, and ego intentions. They are then fed into importance classifier and captioning decoder respectively. Please note that we predict the importance level of all objects in the scene, but only predicts captions of important objects. This filtration of non-important objects uses ground truth importance level during both training and evaluation phases. Such an approach ensures a fair comparison with other captioning baselines, which have been modified to similarly exclude non-important agents based on the ground truth importance level. To obtain the ground truth of the 5 annotators importance level, we use ground truth as the mode of only importance annotations. That is, if 2 out of 5 annotators deem an object as important, we take the mode of only 2 annotators data and not all 5. This is done to not underestimating an agent's importance. In case of multiple modes, we take the highest importance level as the ground truth importance. Finally, the training uses a weighted sum of importance classification loss and captioning loss. For the importance classification, we consider 3 baseline methods: OIE, Interact, and IOI. All these methods leverage only 2D features. OIE is a 2-stage framework leveraging 2D features to generate object tracklets from videos as object proposals and then classifies their importance. Interact leverages interactions using GCN to obtain importance classification. IOI is a GCN method to explicitly model the appearance and motion of objects in the scene. Results show that our joint model leveraging 2D plus 3D features outperforms the baselines for both binary classification and 4 classes classification across all metrics. For the captioning, we consider 2 baseline methods, SNT and scan-to-cap. SNT leverages only 2D features to generate captions, while scan-to-cap leverages only 3D features as point clouds to obtain object proposals and relational graphs to predict captions. Results show that our model leveraging both 2D plus 3D features outperforms the baselines on CIDR and root scores. In conclusion, we introduced a multi-modal dataset Rank2Tell for joint importance ranking and reasoning in urban traffic scenarios, focusing on intersections. It's a first multi-modal dataset that captures dense annotations of various semantic, spatial, temporal, and relational attributes of various agents in the scene. Also, it captures the diverse natural language explanations. We developed a joint model and also established a benchmarking suite on Rank2Tell for importance ranking and captioning. The next steps will involve leveraging dense annotations of Rank2Tell with reasoning abilities of LLMs to predict importance and reasoning, as well as develop a model to generate diverse captions. With this, I conclude my presentation and thank you for your attention.